So then this next problem is a little more complicated. I have myself a runway. Okay. Oh, a little bit too high. Let me do that again. I have myself a runway. Okay. The runway has a length of 3 kilometers, or 3,000 meters. What's happening is I have a plane that's going to accelerate at a rate of 3 meters per second acceleration down the runway. It's going to reach a point, referred to the point as no return, and then it's going to slam on the brakes for the remaining section, and it's going to slow down at a rate of -2 meters per second. Okay? Cool? So in order to solve what you're looking for is the amount of time it takes to get to that point of no return. Okay? So what I'm going to do is I'm going to do this. The first thing I know is I know that this distance, and we'll call this delta x plus, meaning the displacement with a positive acceleration, plus delta x minus the section of track, the displacement, with a negative acceleration. Okay? I know when I add those two values together, plus delta x minus is equal to 3,000 meters. Just doing the conversion right off the bat. Okay? Now, the next thing I want to do is I'm looking at time. So I need equations with time in it, or at least some equations, so I can relate things together. Well, I'm going to make a list of my kinematic equations on this side. The first one, V final is equal to V initial plus AT. Okay? Then V final squared, I'm just going to jump the gun right on there. V initial squared is equal to 2 times my acceleration times my change in position. Okay? And then lastly, the kinematic equation. I'm going to simplify it slightly by saying delta x, which is my displacement, is equal to V initial t plus 1/2 AT squared. All I did was, if you remember the true equation, that's x final, this is x initial, I move them together, and I have x final minus x initial, which is nothing more than displacement. Okay? Cool? And from there, I'm going to have to use these equations in combination in order to solve this problem. Well, in addition, I need more information. I don't have enough. Apparently all I have is a final position for the entire motion, which isn't going to work anywhere in this equation, and I have accelerations. But I have more than that. Put those accelerations back on the screen. For delta x positive, delta x negative, I'm going to build a table. Okay? I have acceleration, which I do know. Can you see that? Yes. I have initial velocity, final velocity, and change in position. Now, we don't know the change in position, and it's off the board anyway. These are the key ideas I'm looking for. The other one being time. We don't know that one yet. But I have an equation for the delta t, so I'm not going to put it on there. I don't know what time is, but that's near the very end. So here's the other variables that I'm looking for. I do know the acceleration. This one's going to be 3 meters per second. This one's going to be -2 meters per second. Negative because it's accelerating in this direction. Positive because it's accelerating in this direction. Velocity initial. My initial velocity for the beginning of the motion, 0 meters per second. That's how fast this plane is traveling when it gets started. Well, you can't board a moving plane, so it's got to be 0. The final velocity, I don't know. But what I do know is that the final velocity and the initial velocity for the second half of motion are identical. How fast it is at this point is how fast it is initially for this motion on. Okay? The final velocity is 0 meters per second. Okay? So I do know some information here. What I'm going to do is I'm going to look at what I know and apply it to equations. Well, this one looks okay, except for in both of these, I don't know my initial or my final, whichever one it is, or my time. I have 3 terms, and of those 2 terms, I really don't know an answer. Over here, I've got 3 terms, but in this case, I do have an idea about this, and I do have an idea about one or the other. So, maybe. This one, same situation as above, with the exception of the first problem. If you look at it, delta x is equal to, drops off, equals this. So we're going to look at that one first. But what I want to do is I want to tie this in to this. And how I'm going to do that is by using this equation. Okay? So for the first bit of motion, okay, for this section of motion, that's why I'm writing this over here, I have v final minus v initial is equal to 2 times my acceleration times delta x plus. For the second half of motion, you have v final squared minus v initial squared 2 times the acceleration times delta x minus. And parentheses on there. Okay? First half of motion, this term goes away. Second half of motion, this term goes away. Also, this term and this term are equal to each other. Okay? This one may have a negative sign on it, but these terms are equal. Okay, so what I can do from there is I can say that v final squared is equal to negative 2a delta x plus. Okay, which means that for this one, I can plug in this for this. Okay, so I'm left with negative 2 times delta a, or not delta a delta x plus is equal to 2 times a delta x minus. And normally I don't put in the accelerations until the very end, but I do want to make sure that I keep them separate from each other. So these negative signs go away. I'm left with 2 times 3 meters per second times delta x plus is equal to 2 times negative 2 meters per second times delta x negative. Oh, I forgot. No, it's there. It's interesting. No. I screwed up here. My apologies. That isn't a negative term. That negative term disappeared when that term went away. So this stays negative. My apologies. Okay. The reason why that's important is because these negatives have to cancel each other out. So I'm left with negative 6 meters per second times delta x plus is equal to, and I'm going to have to erase some of this stuff, negative 4 meters per second delta x minus. Okay? So now let me erase some of the stuff on top and we'll finish up. Okay? Oops, I shouldn't have erased that. That one was kind of important. But I do need the space. Okay? So now I'm left with 6 meters per second times delta x plus is equal to 4 meters per second times delta x negative. Okay? Cool? So I'm left with delta x plus is equal to 4 meters per second divided by 6 meters per second times delta x negative. Okay? Cool? Now, that translates into the meters drop off, the seconds drop off, so I'm left with 2/3 x negative is equal to delta x positive. Now, if you remember, and I erased it, and I wish I didn't erase it, that delta x positive plus delta x negative is equal to 3,000 meters. Oops, not 300 meters, 3,000 meters. Okay? So that means that if I substitute this in for this, I can get my length of runway. Okay? So I end up with 2/3 delta x negative plus delta x negative. I'm going to be glad to quit saying delta x negative and delta x positive. Okay? So if I add this to this, remember that this is 1, so we translate to 3 over 3. So I'm left with 5/3 delta x negative is equal to 3,000 meters. Bring the 3 over to that, bring the 5 over to that. I end up with delta x negative is equal to 3 times 3 is 9, plus all the zeros, divided by 5 and 1, so it's 5 meters. So that means that delta x negative, that goes into 9 once, leaves me with a 4. 40 is 1,800 meters. So that means that this length of track right here is 1,800 meters. Well, by process of elimination, which I guess it's not, but just using this plus this equals this has to be 1,200 meters. Okay? Awesome. That is excellent, because now I have lots more information we'll use. So, looking at things, we had the equations V initial is equal to V final plus AT. We are left with V final squared minus V initial squared is equal to 2 times my acceleration times my change in position. And finally, x final, or delta x, is equal to V initial t plus 1/2 AT squared. Now, I'm looking for the amount of time that it takes to get from here to here. The amount of time it takes to the point of no return. Not for this motion. So, from this point on, all of this data is irrelevant. All I'm concerned about is this motion. Well, I need to find out how fast that plane is traveling at that point. Because, well, hold off. I think I've jumped the gun. I think I can solve it with this one. 12,000 meters is equal to, my initial velocity in this case is 0 times t is equal to, or not equal to, plus, there's my equal to, 1/2 3 meters per second t squared. Okay, this term goes away. I'm left with that, so that ends up with 1,200 meters is equal to 3/2 meters per second. I'm going to do that times delta t, or t squared. Bring that over to the other side. I've got 2 times that, which is going to give me this divided by this, and that's going to be seconds squared is equal to t squared. Well, that translates into 8. 24 and 3, that gives me 800 seconds squared is equal to t squared. Okay, so at that point, I've got the square root of 8 times 100 seconds is equal to t. So that then translates into, going up top, because I don't have any room below, 10 times the square root of 8 seconds is equal to the time of no return. Okay? So that's the answer for that. A very long problem. A couple of things you had to figure out, and obviously there were things that I missed and I didn't pay attention to, but it's doable. Cool?